Recording. Okay. So today we are going to cover three topics. One will be the work done by the gravitational force, another is the work done by spring force, and the third one is the power. So let's begin on the first one. And this is about an object that you are throwing it out, like you are throwing it upward. Okay. So once you throw it upward, you are throwing it with some initial speed. Just because of the initial speed, there is kinetic energy in that, right? When the object goes upward, it slows down and eventually comes to a rest at some point. When it comes to a rest at some point, right there, the kinetic energy is zero. When it falls backward towards the earth, it gets again the kinetic energy. So as you are seeing, we are considering the trip in which the object is just going upward. So you are seeing on the right side that when you throw object, like this is an object, and here there is only one force acting on it, and that is called gravitational force, which is the weight of the object. If the object has covered a displacement from here to here, and that displacement is upward, right? Upward. Based on these two vectors, when we are looking at the force vectors here and the displacement vector here, we already see that the angle between them is 180. So the work that I'm getting is going to be negative work done. And just because we already discussed the object, when you are throwing it up, it has a lot of kinetic energy. And when it goes upward, the kinetic energy decreases, and eventually it is becoming zero when the object stops up there. So the gravitational force is doing negative work on it. So when I'm looking at the work done by the gravitational force, it will be Fg times d. And then you have cosine 180. 180. So just because of this cosine 180, we get negative Fgd. Either you write Fgd or you write mg d. This is the negative work done. Okay. So, but other case, when you are considering the object, you are falling from the top of a building. So the object goes downward. The gravitational force acts on it. It is also downward. So like that, the object weight is downward. It covered displacement downward. You know that the two displacement and the force, both of them are parallel. The angle between them is zero. When you put them in this equation, what you get is Wg is equal to mgd, because the cosine 0 is 1. So the work done by the gravitational force in this case is positive, because when you let the object go from the top of a building, right there, since you are holding the object initially, right there it has zero kinetic energy. But when you let it from your hand, as it goes downward, it continuously accelerating, and the speed becomes more and more until it reaches the surface of the earth. So this work done is positive because more energy is transferred by the gravitational force to the object. So this is positive. Now, the situation we want to discuss, now you are not letting the object go, like not you are throwing it or not you are dropping it, okay? It's not the case now like that. Here I'm discussing another case in which you are controllably moving the object upward or moving it downward. It is still controlled. For example, you are seeing this marker and I'm holding it in my hand. I'm moving it upward. So my applied force is upward like this. The gravitational force, because of the weight of this marker, it is downward. Okay. So there are two forces involved now. One is applied by my hand, and another is applied by the gravitational force. So if I move it upward, one of the force does positive work, another force does negative work. When I'm moving it downward, again, one force does positive work, another force does negative work. So let me ask you this question, and I want you to understand if this point is clear to you. If I'm moving the object upward, in which direction my hand is applying the force?
Upward.
Upward. And if I'm moving the object like as it is right in my hand, and I'm moving it downward like this, in which direction my hand is applying the force?
Upward also.
Upward again, because I'm supporting this object and I'm not pushing it downward. I'm supporting. This is a support force. So in both cases, it is upward. So when you move the object upward, this is your applied force, and here there is the gravitational force. Let's you move the object upward by a displacement d. Okay. Now we want to see how much work is done by your hand. Work done by the applied force is FA d, and you saw these two are parallel, so therefore cosine angle between them is 0. So it is FAD. A is coming just for the applied force. Another one is the gravitational force. We know the angle between them is 180, which we did in the previous slide, and therefore the work done is minus mgd. But if I'm moving this downward, let's say it is moved downward by a displacement d1. So again, the angle between d1 and the applied force is 180, and the angle between d1 and mg is 0. So the work done by the applied force is negative, while the work done by the gravitational force is positive. Okay, so in that case, it will be FA d cosine 180 minus FAD, and the gravitational force, it is going to be plus mg. So it is the positive work and negative work, it will be mainly depending on in which direction the object was moving. Now what we want to do is understanding the complexity of the work done by the gravitational force and the applied force. What we want to do is to bring the link between the energy and work, which was the work energy theorem. So we know that the work done, the total work done, is equal to the change in kinetic energy. So now I'm going to combine this. Change in kinetic energy is equal to the work done by the applied force plus the gravitational force. And from there, I'm going to move ahead and make other conclusions. So suppose that when we are looking at the work energy theorem, we see that change in kinetic energy is equal to the total work. You can say W net. And the net work was coming from the two aspects. One was the work done by the applied force, and another one was work done by the gravitational force. Here we see that the change in kinetic energy, it is Kf minus Ki is equal to Wa plus Wg. And this slide, I'm discussing a very special case. I'm saying this. Here you have this marker. It was initially at rest. So the kinetic energy is 0. I moved it downward, brought it back to this lower position, and then again, its kinetic energy is 0 because it is at rest here and it was at rest up there. So at both end and the start of the journey, the marker is at rest. So the velocities are 0. Therefore, the initial and the final kinetic energies are 0. So I'm saying these kinetic energies are 0. Once that is the situation, that would mean that the work done by the applied force is equal to negative of the work done by the gravitational force. Means one work was done positive, so it transferred the energy to the system. Another work was done negative, which took the energy out of the system. That's what it means. Okay. So this statement you can also apply if the object was going with a constant speed. You say the object here and here, both of them are still going with the constant speed, but just your hand is controlling it. If you let the object go, it will be accelerating by the gravitational acceleration. But if you control it, like move it downward controllably, right here and lower, at both cases, the velocity is zero. Sorry, the velocity is constant. Therefore, the initial kinetic energy is equal to the final kinetic energy. The term will also cancel out, which would also mean the applied work is equal to the negative of the gravitational force. Any question, guys? Okay. Let's do this problem here. An object is pulled along a frictionless rim, but the object starts and ends at rest. Thus has no overall change in its kinetic energy. A rope pulls a 200 kilogram sleigh up a slope at an incline angle 30 degrees through distance 20 meters. How much work is done by each force acting on the sleigh? So in this work, this is the kind of situation which you can apply and understand this work done by multiple methods. But I will be going with one of them. And going just putting this close to the what we have learned in chapter 5 and 6. So suppose this is the sleigh, and the sleigh is pulled up along the track by this rope, and there is a tension force in that. We also know that there is the weight of the object, which is downward, okay? The sleigh is moved from here by a distance d, okay? Here this inclined plane is making an angle 30. We are resolving this in components. It is 30 again, theta, and here. This is mg cosine theta, and this is mg sine theta. You have two forces, mg cosine theta and mg sine theta. And also you have a normal force coming from the plane, a normal force. All these forces we have. And they're asking us to determine the work done by all forces. Just understanding the concept of the work, I'm asking you a question. Suppose this is the direction of the displacement because the object is going upward. This is the direction of the displacement. How much work is done by the normal force? How much work is done by the normal force?
Is it zero?
It is zero because the displacement and the Fn, both of them are making 90 degrees with each other. So cosine 90 is zero. So therefore, we are getting the normal work done by the normal force is zero. Now in this case, we have mg cosine theta. And how much work is done by the mg cosine theta? Are you there at all?
It is also zero.
So then just keep responding.
Yeah, we are thinking.
Okay. How much work is done by mg cosine theta?
Zero.
Zero.
That is zero again. Mg cosine theta, that is giving us 0 work.
Yes.
Now, we need to look at the work done by the tension force, okay? So the work done by the tension force, it will be T d cosine theta. But the cosine theta between the d and d is 0, so therefore we will get Td because cosine 0 is 1.
1. Yes.
The T, we don't have any information about that. We don't know how much the T is, okay? One approach is this, to determine T and look for the work done by the T. But we don't know, it's a little bit lengthy and I can tell you how they need to be done. For example, resolving the forces from this, we can see the T is upward, minus mg is downward, and we have the object supposed to be accelerated upward by some amount. But if the object was initially at rest and afterward at rest, so how much is the total acceleration there?
0.
0. So the acceleration is 0. Therefore, the tension is completely balanced out by the, sorry, mg sine theta. I should be writing it sine theta. Mg sine theta. Okay. So T is equal to mg sine theta right there. Once you know that, you bring that and put it mg sine theta times d. Mass is known, g is constant, theta is known, t is given. So all these things are known. We can determine the work done by the tension force. This is one thing. Another is that we need to determine how much is the work done by the sine theta itself, mg sine theta. So that will be the work done by the sine theta. First of all, the force is mg sine theta. Okay. Then the displacement in this one, both of them are pointing in the opposite direction. So the cosine angle between them is 180. So 180, it is giving me the sine theta for that.
0. 0.
So it's negative the tension.
Sine 180 is 0, right?
Yes. Sine 180 is minus 1. So it is going to be minus mg sine theta d. We have equation 1 here, and we have equation 2 here. If we add the two works, how much do we get?
0.
0. So then net work done on the sleigh is 0. And that can be also seen when you are looking at the change in kinetic energy, which is kf minus ki. How much is the initial kinetic energy?
It's 0.
And how much is the final kinetic energy?
0 as well.
0. So you can also see the net work is 0 from the kinetic energies, as well as using this equation. Both methods are fine, whichever you use. Okay, so by this I'm getting into the second topic that I want to cover in this lecture, that is about the Hooke's law, the spring force. Are you guys familiar with it from the high school?
Yes.
Okay. So let me establish a little bit background, and then we will be going a little bit more to understand challenging equations.
Sure.
Yes.
Key here is a constant or no?
What is that?
Key minus key x. Key here is a constant or no?
K, yes.
K is a here. I'm explaining that. Here.
Okay.
Wait. Yeah. Here, in this topic we want to cover the Hooke's law. It is the Hooke's law is applied for the spring. So, based on Hooke's law, it says that whenever you pull the block in either direction from this equilibrium position, okay, so if the block was right here at the equilibrium position, which is here, like the block and the spring both are at rest, having no push or pull, at that the force is going to be 0, because the block is at x equal to 0. So when you put the x equal to 0 position, you by default get the force equal to 0. But if you pull the block on the right side to this side like this, okay, we know that this displacement is positive, okay, which is plus x. But we also know that if I'm pulling the block outward, the spring will be trying to bring it inward. So the spring force is going to be inward, okay? If I do another thing, then instead of pulling it outside, I started to compress the spring thisward. And this is considered negative x, because this was 0, consider that origin. So it's a plus x, this is minus x. So when I'm compressing the spring will try to push the block against me, okay, like this. So in this case, we see when the x is positive, the force is pointing to the negative x-axis. When the x displacement is pointing to the negative x-axis, your force is pointing to the positive x side. So all the time, the x, the position in means the displacement, and the force will be pointing in the opposite direction for the entire journey of the block. Therefore, in the Hooke's law, you have this negative sign. Another aspect of this law is to look at, suppose that you have K, which is the constant of the spring. It doesn't change for a spring, but from one spring to another spring, the K is different. Just give me one second. There's more calls are coming. I don't know. Hello? Assalam. Awa. Awa call. The class हम भी आवता. Okay, so there is fx is equal to minus kx. You see here the k is constant for a single spring. Suppose that I give you the value of k is equal to 1, okay? And I give you x equal to 0. What is the force?
0, of course.
0. And if I give you x equal to 1, then what it is?
It's -1.
-1. And if the x was 2, then it will be -2, so on and so forth. By this example, I want to establish that the force, it depends on how much you stretch the block away from the equilibrium position, either this direction or that direction. In any direction you stretch the block, it will be giving you that kind of force. So means the force is no longer constant. So far in the Newton's second law, we used to use F equal to ma, and we said mass of the object does not change and the acceleration is constant. So all the time the force used to be constant. But in the spring force, it is not constant. It depends on the position of the block. So it is a variable force. Now this is the first time we are dealing with a variable force. So let's try to understand how to tackle this and how to determine the work done by this force. So the main method for applying this is here. When you are applying this Hooke's law, we need to make 3 assumptions first of all. The first is we will be considering the spring massless, even though we know the spring has some mass, but we will be neglecting the mass of the spring. Second is, it is an ideal spring, means it obeys the Hooke's law. You may have seen some springs that you stretch it beyond certain limit, it will never come back. So it will not be that situation. The situation will be such that it will be coming back to its original position all the time you disturb it, okay? So it obeys the Hooke's law exactly. The third is, the contact between the block and the floor is frictionless, which is true only for this chapter. Later on, we will bring the friction force between the block and the surface. But for this chapter, we consider the surface frictionless. Suppose we know that the block is since the force is variable force. I cannot understand the variable force, work done by the variable force, by using the equations which I have derived for the constant force. So I need to do something for it, okay? And that something is done here. What you do is that when you are, this is the spring, and here you have the equilibrium position. Suppose that you are pulling this block away from it. What you do is that you say that if I just move the block only by 1 centimeter, even though the force changes, but it is almost the same. So what I do is that I consider an average force for this distance only. Then from the 1 centimeter to 2 centimeter, when I move this, between this, there is again some force, which is a little bit larger, but I can take an average of that again. And so on and so forth. For each segment, you consider this force to be a little bit constant. Even though the intensity of the force increases, means the force becoming more and more, but overall you get a constant force in each segment. Once you do that, what you will do actually, you will determine the work done in this segment, work done in this segment, and work done in this segment. And at the end, you have to add all of the work done during the entire journey. So the equation will be more like this, as you are seeing here, okay? Like this one. When you add all segments, that's what you will get. But even still, there is a little bit error in this. And this is a little more cumbersome to apply because I have to calculate a lot of works. So I don't want to do this. I want to apply a little bit easier method. So now I'm going to apply integration just for sake of derivation. You are not required to use the equation, but you need to use the final product of this. So let me derive this equation first. If you have any question, you can certainly ask that. We know that the work done right here is done by the spring force, so I can write that as the Hooke's law, the spring force, times by which the displacement has, the black has been moved. This is the displacement segment. And initially the black was at x equal to I position, and it been moved to x equal to F position. For the spring force, I'm putting minus kx, minus kx, minus kx. And taking the minus k out because it is constant. xi to xf, x dx. Can someone tell me what we will get from this integration?
half x squared.
Half of x squared. So x squared divided by 2 we get, and then we apply the initial limit and the final limit. So when I apply that, what I get is that half k, and this will be the xf squared minus half k xi squared. And this negative sign become positive. So I want to rearrange this equation now. Okay, just look at this equation because we will be using it. So the work done by the spring is half. I'm moving this because this is a positive term and the final term is negative. So kxi square minus half k xf squared. Okay, this is my equation. Just note that the initial position is first and the final position is last. This will be the equation we need to use. You don't need to understand the middle steps. If you do, it's better for you guys, but you are not required to do applied integration. We understand that. And then later on, we will be using the area under the curve for the variable forces. This will be the equation that we will be using for the entire spring work done by the spring. Okay. Suppose again that the situation is similar to like the work done by the gravitational force, and I'm holding the block and I'm pulling it out. So when I'm pulling it out, I am applying my force in that direction. The spring is applying a force on me in the opposite direction. Okay. Suppose in that situation, the total energy is 0, means the total kinetic energy of the block is 0. The block was initially at rest and afterward at rest. So we get the applied work done by the applied force is equal to the work done by the spring force. Exactly like this equation here. Like whenever you are pulling the force out, the block outward, you are applying a force, the spring force is opposite direction. If you are pushing the block, you are applying your force in this direction, the spring force will be in opposite direction. So all the time, your applied force and the spring force are completely in opposite direction. By the work energy theorem, that tells us if the net energy is 0, then that means that your work done by your applied force is equal to the negative of the work done by the spring force. Here we are applying this this theorem, like which I just derived, to this checkpoint. Suppose there are 3 situations. The initial and the final positions respectively are given here. Like in the case A, the initial position is -3 and the final position is 2. Is the work done by the spring positive, negative, or 0? What is your take on it?
For C, it's 0.
For C, it is 0, but how about for A?
The initial. For A, it is positive.
Is it positive?
They say the initial is the first value.
Yes.
So when we subtract 2 squared from -3 squared, that's
yeah.
positive.
So 9 minus 4 will give us 5. That's what you mean, right?
Yeah.
Okay, so that will be positive. How about for the B?
Negative.
Negative. And for the C, the student already said it is 0. So yes, that's the case. Okay, in this problem here, a cumin canister of mass 0.4 kilograms slide across a horizontal frictionless counter with the speed 0.5 meter per second. If then runs into and compresses a spring of mass constant, a spring constant K 750 Newton per meter. When the canister is momentarily stopped by the spring, by what distance d is the spring compressed? Here we are going to apply the work energy theorem. We know the change in kinetic energy is equal to the work done. And here we see that the work is done only by the spring force. There is no other force involved. So I'm going to put as a Kf minus Ki, final kinetic energy minus initial kinetic energy, is equal to the work done, which is this, half Kxi square minus half Kxf square. Okay? When the canister was away, it has some initial kinetic energy, but when it is compressed the spring and came to a stop, then the final kinetic energy is 0. So final kinetic energy is 0 right there. For the spring part, when the canister was not in contact with the spring position was x equal to 0. So the initial position of the spring is 0. But afterward, when the spring is compressed, it has some compression that we are calling it xf, which you can also put as a d as it is required in the problem. Just for the kinetic energy, I'm putting the equation half mv square and half k xf square. The negative sign will cancel with negative sign, half will go with the half, and then what we need to do is to solve this for the xf. So xf is equal to m vi square divided by k under the square root. Now we see the mass of the spring, the canister is given 0.4. Initial velocity of the canister is also given, which is 0.5. And we know the spring constant, which is 750 Newton per meter. It is also given. Everything is known by now. So we just apply that and determine the xf. Okay? Like this. Okay? So by now, you guys got familiar with the okay, what is that? Okay, let me see. You guys know that the spring force is constant. We already tackled one problem on the based on the spring force, which was variable force. Similarly, more variable forces can also occur, and we need to solve them. Here, what we need to do is that instead of going with the integration, we should be looking for the area under the curve. For example, this example is given to you, and this is a little bit complex example. It's not easy one, because the force is not a spring-like force, is not a constant force. So in that, the best method is that you are going to divide the area under the curve in some geometrical shape for you, which you can determine the area easily. For example, rectangle area, which is side by side, triangle area, half base times perpendicular, and the square area side by side. So we need to look for the triangle, rectangle, and such shapes like that. Look at the area under the curve and determine the work done. For example, this particular example, I can split in few sides. You'll see the lower part is a rectangle. You see this one. This is approximately, like if I do this, this will be approximately rectangle. You can also make this as approximately rectangle, and the rest, this area will be a triangle. Okay, so then you can determine the area under the curve based on that. For example, this is one of the problem appeared in major 181. I'm asking you guys. It shows four diagrams, and the four diagrams, the x-axis is the displacement and the y-axis is the force. You need to rank them based on from most positive work to the most negative work. So sometimes the students get a little bit confused what could be the positive work in the terms of the diagram. So look at this diagram. I'm solving this now. This is the triangle you see. You know that if this was your x position, and this could be a zero line. So above that, the force is positive. So you got the force positive, on the x-axis you got the displacement positive. So when you get the displacement positive and the force positive, you multiply both of them and divide by 2, then you get the area of a triangle, which is positive. But for this part, which is below the x-axis, you see the force here on this axis is negative, while the displacement here is positive. So one side is positive, another side is negative, and when you multiply both of them, then what you will get, that will be negative again. So in a nutshell, above the x-axis line, that will be considered positive area. Below the x-axis line, that will be considered negative area. Okay, just guys, tell me, which of these diagrams give you the most positive work?
It's B.
E.
Okay, and then after
Then
that,
A.
after B there is A, and after A there is what?
C.
C.
Look at C and D. So the C, you think C is giving us negative, but not as much as the D, right?
Yes.
Okay, and D is most negative. Yes. So this is the ranking, this is the ranking problem. You did it. Okay. But this I'm switching to the very last topic. I'm touching this, the power. The power is the rate at which you do some work. You are applying a force, you move the car by some distance, so you did work. But it now depends whether you move this in 1 minute or it in 1 second. So the person who moved it in 1 second, he has more power than the other guy. So the work could be the same, means the same force is applied, the same distance is the object has been moved, but the time in which the object has been moved could be different. So the shorter the time taken, the more power the person will possess. Okay, so the power is the work divided by time interval. So this is the average power, but most of the time we are concerned about the instantaneous power, like the average acceleration and instantaneous acceleration. So we change the derivative, the delta, to the derivative for the instantaneous, because the time interval which we consider is extremely small. So dW by dt is the instantaneous power for our case. Now in the last slide, suppose that when you are applying the push to something and your applied force was constant, you didn't change the force, and you also didn't change the direction of the displacement with respect to your applied force. The direction is also the same. So the only change is now coming, it is because in the displacement, if the object was here and you are moving it in that direction, So if it was at x equal to 0 position, later on you found it at x equal to some non-zero position, which is a positive number. But your applied force was in this direction, and the displacement is also in this direction. Both of them are going in the same direction. Theta doesn't change, the force did not change. The only thing with respect to time has changed is the position. So therefore, when you apply the derivative is going to be applied only on the x term here, which is the displacement, right? And we know dx by dt, what it is. Dx by dt. You don't know it?
Velocity.
Velocity. So dx by dt is our velocity, and when we put this as a fv cosine theta, we already apply another definition of the dot product. A dot b is equal to ab cosine theta. So if I know the fv cosine theta, it can be written as f dot v. So now if I know my force and I know the speed by which the object has moved, I can determine the power. This is another way of approaching to it. Since from this definition, can someone tell what will be the unit of the power?
Newton meter per second.
You can go with that, but what is the unit of joule? What is the unit of work? That is joule, right?
Newton per second.
Yes.
So this is the joule divided by second. So joule per second you can call it, and sometimes you can also call it watt. So most of the time we will be using watt, okay, which is joule per second. Okay. Like when you go to a shop and you're buying a bulb for your home, and you are looking for either 60-watt bulb or 100-watt bulb. So actually what you are looking at the bulb which consumes that many joules of energy in 1 second. If it was 60 watt, it will be able to consume 60 joules of energy in 1 second, which is 60 watt. There are various units of the power, like the joule per second is one, the watt is another one. Here, horsepower is another one, which is mostly used by engineers. So 1 horsepower is equal to 746 watt. This is also a unit, okay? 1 kilowatt hour is mostly used when you are looking at the electricity bill. You say that I have consumed 3 units of electricity or 100 units of electricity. So when you are calling that unit is 1 kilowatt hour. So you can look at this slide level. In this checkpoint here, a block moves with uniform circular motion because a cord tied to the block is anchored at the center of a circle. Is the power due to the force on the block from the cord positive, negative, or zero? So the situation is like this. You have the circle, there is a cord, and it is tied to the center. We know there is a force in the cord, there is tension to the center. If it was going counterclockwise direction, in which direction the velocity will be? If it was going counterclockwise, in which direction the velocity is going to be?
Negative for the x-axis.
Okay, but if it was, this is the circle, right? Counterclockwise. So means here, at this point, if I'm looking at, the velocity is going to be always tangent to it. So this is the direction of the velocity.
Yeah,
okay?
positive y.
Yeah. So now I'm looking at the power. We know the power is F dot V, but the force is tension here. And the V and the angle between them is how much? How much is the angle? 90. So cosine 90 is 0. The power transferred by the applied force is equal to 0 in this case. That's what you have. This is the very last question I want to solve, and then we're going to start. Here you have two forces, force 1 and force 2. Acting on a box as the box slides rightward across a frictionless floor. And the force 1, what is this, man? Yes, guys, quickly raise your hands here. Okay. Is there any other student who is still there? Ahmad Abdullah Bawazir, Ali Jassim, Hamza, Hussein, Osama, and Yahya.
Yes, doctor.
Okay.
Yes, doctor, I'm here.
Okay. Okay. In this problem, here we have two forces, F1 and F2, acting on a box as the box slides rightward across a frictionless floor. Force F1 is horizontal with a magnitude 2 Newton, and F2 is angled upward by 60 degrees to the floor and has magnitude 4 Newton. The speed V of the box at a certain instant is 3 meters per second. What is the power due to each force acting on the box at that instant? And what is the net power? Is the net power changing at that instant? So we need to first understand the force, then determine the power for force, then power for the second force, and then once we know the two, then we can combine them. So let me, you guys need to help me, okay, here. The power 1, the power of force 1. What is the formula for that?
Work over time.
Work over time, but here we derived another formula later on. That was F dot V, right? F1 dot V. And we know that F1 V cosine. What is the angle between the velocity and F1?
180.
180. Okay. So here I'm going to put the values of F1, that is 2 Newton. And the velocity is, how much it is?
3.
3. And cosine 180. So we get it minus, just minus is coming from 180, cosine 180, and this is 6 watt. Okay, this is power 1. Now for the second force, we again apply the same formula, which will be F2 V cosine. What is the angle between F2 and V?
Will be cosine 60.
Cosine 60, okay? Cosine 60. So the force F2 is how much?
6.
The force is 4 Newton, right?
Yes, 4.
Force is 4 Newton, and here we have the V is 3, and cosine 180, how much it is? Sorry, it was 60. Half.
Half.
Okay, so it cancels out, and we get 6 watt. Okay, now they're asking for how much is the net power, so we just need to add them. The net power, the total power is 0 because it's a plus minus 6 and plus 6, so we get 0. At the end, they says that is the net power changing at that instant? Is it depending on time?
No.
No, so it's not changing. So with this, we are done with the lecture. You guys are free to leave. I'm beginning another lecture
Doctor,
Yes.
I forgot to make attendance the form. Can you open it
When did you join?
from the first minute?
Let me see.
Should we do it again or it's
No,
enough?
you don't need to. You don't need to. First, I need to show this guy when did he join, and then. Okay, so there is no one who joined after 12.2, so yes, I can open the file for him.
Thank you.
Yeah.
Doctor,
Yeah.
I forgot to
What did you forget?
make an attendance.
Okay.
Sorry for that.
Doctor, until now it's not open.
Yeah, that's. I need to go into internet. There is asking lots of passwords. Okay, let's.